to discuss linear differential equations. But before we do so, let's review some properties of bifurcations that we found in our last lesson. To get some intuition behind the examples, let's consider the following differential equation. dy dt equals f of y, where f of y is the quadratic y squared minus 2y plus mu. Here mu is a constant. We see that the graphs of these solutions become very different as we move from the constant mu equals 0 to mu equals 2. This is because the zeros of the quadratic polynomial f of y yield the equilibrium points. These are y0 equals 1 plus or minus the square root of 1 minus mu. These are real numbers if and only if mu is less than or equal to 1, and they are complex numbers otherwise. Hence, there are no equilibrium solutions to our differential equation whenever mu is greater than 1. This explains why the graphs look very different as we move from mu equals 0 to mu equals 2. There's another way we can see this. It's called the bifurcation diagram. This change in behavior of solutions is what's called a bifurcation value. In this case, things change when mu equals 1. A plot of the phase lines versus the parameter mu is called a bifurcation diagram. In the slide here at the bottom, you can see that we're plotting on the horizontal axis the parameter mu, and on the various vertical axes, we're plotting the phase lines. You can see that the dots are the equilibrium points. These are the y sub zeros as a function of mu. Notice that as mu gets larger, these 2 points, the y zeros, get closer and closer, and at mu equals 1, they lie on top of each other. But for mu greater than 1, there are no equilibrium points. This is because the y zeros are no longer real numbers at this point. The following is a quick way to determine the bifurcation values of a differential equation. Let's consider an autonomous differential equation, dy dt equals f of y, where perhaps this function f of y depends on a collection of parameters. Let's call them collectively mu. Then mu is a bifurcation value for our differential equation if and only if there exists a complex number y0 such that f of y equals 0 and f prime of y equals 0. Let's consider a couple of examples. First, let's go back to the example from before, f of y equals y squared minus 2y plus mu, where mu is a constant. We'd like to find all solutions to the simultaneous equations f of y0 equals 0 and f prime of y0 equals 0. First, we'll compute the derivative, f prime of y, and set it equal to 0. We'll find that y sub 0 must equal 1. Plugging in y sub 0 to f, we see that f of y sub 0 equals mu minus 1. This equals 0 only when mu is equal to 1. So we find that our differential equation, dy dt equals y squared minus 2y plus mu, has bifurcation value mu equals 1. Now let's consider a slightly more complicated quadratic polynomial. F of p equals k times 1 minus p over n times p minus a constant c. We can compute the derivative f prime of p, which equals negative 2k over n times p plus k. We see that this derivative equals to 0 only when p sub 0 equals n over 2. Plugging this back into f, we find that f of p sub 0 equals k times n over 4 minus our constant c. So, setting this now equal to 0, we can solve for c, and we find that our differential equation has bifurcation value c equals k times n over 4. Today we're going to discuss linear differential equations. And to do so, let's start with a motivating set of questions. Let's say that we wish to invest $1,000 for the coming year. There are two banks that we have the possibility of investing with. Bank A will give us an interest compounded quarterly, whereas Bank B will give us an interest compounded daily. The rate of interest is determined by the Federal Reserve Bank, let's say perhaps at 8% annual percentage rate. The question is, which bank will give us a better return on our investment? Let's try to make this a bit more precise by defining some of the notation. Let S of t denote the sum of money in the bank at time t in years. Let's say that this interest rate R is compounded in times per year. That is, n is equal to 4 if we have compounding quarterly, and n equals 365 if we're compounding daily. For each round of compounding, that is, we have t goes to t plus 1 over n, we must add a certain amount of interest. In this case, we'll add r over n times the amount s. So the change in our sum of money, that is s of t plus 1 over n minus s of t, must come from the interest. This equals r over n times s. Bringing everything to one side, we find that s, evaluated at t plus 1 over n, must equal the factor 1 plus r over n times s of t. Now, as n gets larger and larger, this quantity that you see on your screen becomes very familiar. That is, the expression 1 plus r over n raised to the n gets very close to looking like e to the r, or exponential. So s of t plus 1 looks like e to the r times s of t. We'll say that our amount is compounded continuously if n looks very large. That is, if n increases without bound. Let's put all of this into a table so we can see some numbers. When n is equal to 4 and our annual percentage rate, r, is 8%, then we see that the ratio s of t plus 1 divided by s of t is equal to 1.088243. When n is equal to 365, our ratio is 1.08328. And when n increases without bound, morally when n is infinity, we have 1.08329, almost the same as when n is equal to 365. Now here's what this means. If the original investment, maybe S of 0, was $1,000, then we would earn $82.43 from Bank A if we compound it quarterly, but we would earn $83.28 from Bank B if we compound it daily. This means that Bank B gives us a better return on our investment. Now let's maybe think of this using a slightly more general expression. Let's say, similar to before, that S of t is the amount of savings in the bank at time t in years. Let's say that this interest rate R is compounded n times per year, and that we wish to add an extra amount B per year to our nest egg. For each round of compounding, remember that we'll add R over n times S in interest, and we'll also add B over n by adding this extra amount. This means that the change in the amount of money we have divided by the change in time will simply look like S of t plus 1 over n minus S of t divided by 1 over n. Of course, when you divide by 1 over n, you're just multiplying by n. And this equals R times S of t plus B. We can actually compute that the exact value of this so-called initial value problem is the expression that you see on your screen. We won't worry about discussing this any further today, but let's simply say that as n increases without bound, morally as n equals infinity, then our annual percentage rate will actually give us a differential equation. We have ds dt is r times s plus b, and so by using the approximation we had earlier, that is 1 plus r over n raised to the n looks like e to the r, then we can actually write down an explicit solution to this differential equation. Here's a motivating question. Is there a different way we can solve this differential equation? This is what we're going to discuss today. Let's remind you of some definitions we had from before. Recall that a first-order differential equation is an equation in the form dy dt equals f of ty for some function f. A solution is a function y of t such that y prime of t equals f of t comma y of t. We'll say that this equation is separable if f is the product of two functions g of t times h of y. Such an equation is said to be autonomous if g is a constant. We'll say that this equation is a linear differential equation if f equals a of t times y plus b of t, for some functions a of t and b of t. Such an equation is said to be homogeneous or unforced if b of t is identically zero. That is, f equals a of t times y. Otherwise, such an equation is said to be non-homogeneous or said to be forced. Today we're going to spend some time discussing how to solve differential equations that are linear. That is, dy dt equals a of t times y plus b of t. Here's the main proposition that will help us to do this. Let's say that y sub p is one particular solution to this non-homogeneous differential equation. Then the general solution, y of t, is in the form y sub h plus this particular solution, y sub p, where y sub h is a solution to the homogeneous equation. The second part of the proposition tells us the general solution to such a homogeneous equation. It says that y sub h must equal a constant times the exponential of an integral a of t dt. Let's present a proof of this result. For the first part, say that y sub p and y of t are both solutions to the non-homogeneous equation dy dt plus a of t times y plus b of t. And let's denote y sub h as the difference between these two, y minus y sub p. We can then compute the derivative dy sub h dt, and after some algebra, we find that this is equal to a of t times y sub h, which means that y sub h is indeed a solution to the homogeneous equation. Hence, this shows that y, which equals y sub h minus our particular solution, y sub p, really is in this form for some solution y sub h to the homogeneous equation. Since the homogeneous equation now is an example of a separable equation, we can actually solve it explicitly using the techniques that we've introduced so far in this course. If we start with dy dt equals a of t times y, again, this is the homogeneous equation, we can bring all of the y terms to one side, and we find 1 over y dy equals a of t dt. Now we integrate both sides to find that the log of the absolute value of y equals the integral a of t dt plus the constant. Finally, we can solve for y of t by simply exponentiating both sides. This means, putting all of this together, in order to find the general solution to a non-homogeneous differential equation, dy dt equals a of t times y plus b of t, it suffices to find one particular solution, y sub p. This is what we'll discuss in the next lesson. But for now, let's go back and revisit that interest rate problem we began today's lesson with. Just to remind you, let's let S of t denote the amount of money we have in savings at time t in years. Where initially, perhaps we have some amount saved up, S of 0 equals S naught. Now, let's say that our account accrues interest at an annual percentage rate R compounded continuously. And let's say, moreover, that we're going to add an extra amount of B dollars per year. This means that our initial value problem is ds dt equals R times S plus B, where S of 0 equals S naught. We're going to explain now how to find the unique solution to this differential equation. First, we see from the linearity principle above that because a of t equals a constant r and b of t equals a constant b, then we can explicitly find the general solution, s of t is a constant times the exponential of a certain integral, plus a particular solution, s sub p of t. Simply put, this is equal to a constant times e to the rt plus some particular solution, s sub p of t. We can find one particular solution that works by just choosing something like the equilibrium value. So let's choose the constant s sub p of t, which is equal to negative b over r. This works because the derivative ds dt is 0, and also the expression r times s sub p plus b equals 0. So this is indeed one solution that works for our non-homogeneous equation. So putting this together, we can now find our solution by keeping track of the initial value. We'll find that this constant c must be s naught plus b over r, And therefore, we find that S of t is e to the RT S0 plus e to the RT minus 1 over R times B, which is exactly what we claimed earlier. Thanks very much for watching.